right, so good evening and welcome to tonight's Science Cafe. I'm Mark Kersey and I work over at the LRSM. And I'm excited to introduce tonight's speaker. So Neil Tomson is from the chemistry department here at Penn. And as you can see, he's going to be discussing solar energy, the problems with it, and how to fix them. So without further ado, let's welcome the speaker.
Okay, well, thanks very much for the invitation to come. It's really a pleasure to be here. I love having a chance to talk about a few topics that are, I think, really important to society and where we're headed and what we're doing. And I think they're really interesting problems to work on for chemists, too. So I'm really interested in in the energy problem in general. Climate change is certainly a problem. I think probably by virtue of most of you being at a talk entitled "The Problem with Solar Energy and How to Fix It," that I don't have to convince many of you of our climate change problem that we're encountering. But I'm going to leave that aside entirely for this talk and really try and make an argument based off of the needs for our energy, where we get our energy going into the future. That's really motivated a lot by this idea that's encapsulated in this plot. So we go back 5,000 years, ahead 5,000 years. We have not been using fossil fuels for very long, and we won't be using them for very long. So maybe you're more pessimistic than I am, and you think we're only going to make it for another 100 years or so. But hopefully we last a few more years into the future. And if that's the case, then we certainly need some source of energy that's not fossil fuel based. So where do we get our fuels right now? Most of them are non-renewable sources. So we have here, we have what's available to us in fossil fuel form. That's natural gas, petroleum, and coal. And then we also have nuclear energy in the form of uranium. The numbers shown here are the number of terawatts available from those different energy sources. We can argue about the values. That's not really that important in this case. The important thing here is the order of magnitude of these numbers. So you add these up and divide by the amount of energy that we use per year, which is about 16 terawatts. And this lasts about 100 years. That's not very long. 100 years is not very far into the future. So we really need to think about some other energy source, and we need to think about it soon. Luckily, there are a lot of options for energy. Wind gives us a lot of power. This is 25 to 70 terawatts every year that we could potentially get from wind power. A number of other sources. Biomass is a great one, hydroelectric, geothermal. You'll notice that the big elephant on this slide is solar. 23,000 terawatts every year we could potentially get from solar energy. We only need 16. This is a no-brainer. It really seems like if energy companies are worth a lick, they would be moving towards solar. But for some reason, they're not doing that. All right? If we look at the numbers for how the U.S. uses electricity, then we go back, this is going back several decades. We see that fossil fuels have taken off. This is coal. We're not quite up to date, so this doesn't show the really enormous increase in natural gas we've experienced over the last few years. The important thing that I want to point out here is that renewable energy has been mostly flat. We have seen a little bit bump here at the end maybe, but relatively flat for the last 30, 40 years. And even within that, if we break that down in terms of where that energy is coming from, so it's about 10% of our energy portfolio is coming from renewable sources. About 0.1% is coming from solar. All right, so there's this really odd mismatch. We have a huge abundance of solar energy. You can step outside and get all the solar energy you want. As much solar energy hits the Earth in an hour is what we need to power our country for a year. So why on earth are we only using, why on earth is only 0.1% of our energy profile coming from solar energy? I'd say that's really the problem, is that there's some mismatch, and we need to figure out why, and that can hopefully lead us to a solution. So the problem, the difficulty is the consistency with which we can get solar energy. Up here is the output from a 150 kilowatt solar panel array in California. This shows, this blue line here is looking at how much solar energy you get in one day in June. So this is starting in the morning and going to the evening. Of course, the sun goes down at night, so half the day we don't have the sunshine. But there's still quite a bit of output. The trouble, though, is that this varies a lot by the year. So if you go into the fall, on a cloudy day in the fall, now that output really jumps up and down. If If you go into the winter, then the output drops about in half from what you get in the summertime. So there's this huge variation in how much solar energy we can actually collect based off of these environmental variables and based off the diurnal cycle of the sun. We can't count on that source all the time. So if you're an energy company, you look at this and say, well, why on earth would I want to rely on something that has this much variability in it when all I have to do is dig a hole and light a match? That's what you're competing against, right? So the same thing happens with wind power. This is looking at wind power in Germany in 2012. The range is over 2 orders of magnitude. So you have these huge variations in the amount of energy that's coming from wind power, and you just can't, the energy companies just cannot economically rely on this kind of inconsistency. So as it is, big energy companies will cap their load from renewables at about 20 to 30% of their entire load. They just can't make up the difference. So somehow we have to be able to find some way of changing that equation. And I think the way we think about that is with storage. So as the grid stands now, it doesn't matter what the source is. We can take wind power, solar power, put it into our grid. That'll go through some substation coming from those sources. We'll also be generating energy from a power plant, and that's what we use to feed our electricity needs. What we really need to think about is creating energy storage solutions. So have some sort of intermediary where we can take that wind power and that solar panel power and store that, and then be able to use it when we need it. So that lets us decouple the generation of that power, the harvesting of solar power and wind power, from the time in which it's needed. So we don't have to worry anymore about the sun going down. We don't have to worry anymore about the wind not blowing. So there are several different forms of energy storage, and we have a little bit of a problem of how we pick one and then how we actually store it. So I'm going to go through what the options are, and I'll talk about a couple of general ways of storing energy that I think are hopefully very compelling. So just to orient everyone, energy is the ability for a system to do work. We can think about this happening in a number of different forms. So one is explosives. You can store a lot of energy in chemicals. You give them an ignition and you get a big kaboom. This is particularly important today because it's 5th of November, right? All right, Guy Fawkes Day. So that's one. That's probably not the best option. Let's not store all of our energy in explosives. Another one is things like wood, anything that burns, right? So we see this happen on forest fire scales. We see there's a massive amount of energy there. We can tame that and use it for much more pleasant purposes, like a fireplace. Okay, so a number of different sources here. We of course use fossil fuels for this all the time. Natural gas, it heats our homes and cooks our food. If you live in Western Pennsylvania, then maybe the flame looks something like this. and so there of course a lot of energy in all of these, and all of these sources are chemical bonds. These are chemicals that we can collect and store and use when we want to get energy out of them. I think a really interesting idea is to think about alternative fuels. None of these there's not enough wood to be able to fuel our society entirely, and it doesn't grow fast enough. Explosives are obviously a non-starter. Fossil fuels, we've been talking about how that doesn't really work well. So maybe it makes sense to start thinking about how we can generate alternative fuels. And a lot of people look at this problem. This is a really interesting one. So biodiesel, growing plants, specifically algae, that's a really great one to look at. Growing plants and then being able to convert that plant matter into fuel. That's a really good option. What that does is it essentially it's using solar energy, right? You're taking solar energy, growing the plant, and eventually taking that collected energy and using that for fuel. That's a good option. There is a food versus fuel problem, right? So a lot of this comes from corn now. We take corn and we can turn that into ethanol. So it's ethanol instead of biodiesel, but it's using biomass to create fuel. Another possibility here is to create things like hydrogen or alkane fuels, something akin to gasoline, through direct conversion from solar energy. And people work on this idea of an artificial leaf, where you can essentially just shine light on a material that's stuck in water, and that material will catalyze the disproportionation of water. So you end up forming hydrogen and oxygen from that. You can imagine using the hydrogen by itself, or combining that hydrogen with CO2 through artificial photosynthesis to form fuels. In this case, this first step is starting to get some traction. People are finding out ways to actually generate hydrogen on what's getting close to meaningful scales. The second step here is really difficult. People don't have this one cracked, and specifically stitching carbons together is a pretty tough prospect. That's really what makes nature so amazing is it's found out how to do that extremely well, but we're a little bit behind. So we can start thinking about other fuel alternatives, and I'm just going to leave it at this for now, and we'll come back to that in just a second. So another way we can think about storing energy then is through storage of electricity directly. So not worrying about using electricity to form bonds, but instead just store that electricity as potential energy that can be used used for powering a grid when we want to. On a personal scale, of course, we're very comfortable with the idea of batteries. We have things like personal batteries, AA, AAA. We use car batteries. Those are very common. Lithium-ion batteries, we use those all the time. That's a $15 billion industry is making lithium batteries. So these are all forms of storing electricity and then being able to use it for powering our devices. You can also think, though, about storing energy on a grid scale. Here, supercapacitors is really one interesting concept where you can think about taking an electron and moving it away from a favorable position to a relatively unfavorable position and holding it there. That's really what a battery does. It's just that supercapacitors do this on a massive scale. And in a similar way, we can think about other big battery technologies. And this is showing a type of battery that I'm going to explain the function of in a few slides. This shows you the kind of scale. We're talking about a human scale here and these massive structures that we could use to store relatively large amounts of energy that could then supply our grid. So I'm going to start with talking a little bit about alternative fuels, a few reasons why I'm particularly interested in that and why my lab is working on this problem and how we think about getting around some of the challenges. And then I'll talk then about, oh, sorry. I shouldn't have gone back there. Hit the wrong one. No. And then I'll talk a little bit about some big scale batteries and also a little bit of work that we're interested in. So for all the alternative fuels that I mentioned, I didn't talk about ammonia, but I think ammonia is really a very promising one. So it has a number of advantages over the others, and I'll walk you through those. We generally think about ammonia like this. Ammonia is a fertilizer. So we have it in these large cylinders. It comes in anhydrous form. We can spray that on fields, and that's a great fertilizer. We've since the production of the large-scale industrial production of ammonia was discovered in the early 1900s, our population has grown many times, and that's largely due to the increased availability of food that's made possible by the increased yield from crops that we get by being able to use artificial fertilizer to let them grow. So we have a lot of ammonia. We know how to handle it. Maybe it's worth thinking about whether or not we can use it as a fuel. So the idea here is that we'd use some sort of energy source to generate ammonia, and we can then use that ammonia to power whatever devices or products or homes or whatever we want to power. There's a pretty long list of advantages here. So ammonia can be made from, ammonia is NH3, that's 1 nitrogen and 3 hydrogens. So it can be made from air, which is 80% dinitrogen, that's N2. Also from water then, and we can form it from renewable energy. There are no carbon emissions from burning ammonia. If you burn it, it burns cleanly. It goes to water and to dinitrogen. You can power internal combustion engines with it. So that's a really big advantage because a difficulty in moving to alternative fuels is the prospect of having to change how we build all of our cars. I mean, first of all the cars that exist, millions of cars on the road, and those need fuel to run. And then also the infrastructure involved with car companies retooling and with changing the types of refueling stations we have. So the very fact that this is able to burn an internal combustion engine is really very useful as a way of easing our conversion into an alternative fuel source. It is compressible. It's a big advantage over hydrogen. Hydrogen is touted as a really promising alternative fuel, but the difficulty there is that it's very difficult to get enough hydrogen on your vehicle to be able to take you very far. So people work on this problem. There's some great advances. People have done a really nice job on it. But ammonia is easily compressible. It doesn't take that much pressure. So with the relatively high energy density of ammonia, you can think about fueling up your car in a similar capacity as what you do with gasoline and be able to take a nice long drive with it. We don't have the corrosion or embitterment problems that you do with other possibilities. A big advantage here is we have a national distribution network for ammonia. we synthesize ammonia down here and then transport it up through the middle of the country as a fertilizer. That's a big advantage if we want to think about using it as a fuel. Is we already have all of this built-in pipeline for transferring ammonia around the country, 3,000 miles of it in the U.S. We know how to use it. We synthesize it and consume it on a really large scale, so we know how to handle it and how to do it safely. And we have a lot of storage capacity for it. So I think between the advantages that we get from being able to use it in vehicles, along with our knowledge of how to handle it and the infrastructure that we have for distributing it, this is really a pretty compelling option as an alternative fuel. So what are the disadvantages? Well, toxicity is one, for sure. It's acutely toxic. So if you were sitting in a room, a sealed room with ammonia, then you would die, and that's no good. Nobody wants that at all. Well, some people might want you to die, but that's not for me to determine. So the nice thing, though, is that ammonia is lighter than air. So if you have an accident outside, if a gas tank is leaking, whatever the situation is, the ammonia goes away. And the worst thing that happens is that the fields around you get fertilized a little bit. So it's really a pretty benign byproduct of that process. So the other difficulty is production. That's illustrated here. So as we do it currently, we use the Haber-Bosch process, which is this is what was developed in the early 1900s. Yeah, Haber's he's a nasty guy. That's someone who if anyone knows the story, you'll appreciate just how terrible he is. If you don't know the story, go and Google Fritz Haber. He's an ugly human being, but he did some pretty interesting science. So we can at least appreciate that. He helped develop this process along with the engineer Bosch, who made it feasible for generating ammonia from dinitrogen, what we get out of the air, and hydrogen. And the way this works, I won't step you through the nitty-gritty details, but essentially you heat this up and you pressurize it. The atoms rearrange and you get ammonia out as the product. So for people who know what this is enthalpically favorable. So it's a downhill enthalpic reaction and actually gives off energy. It doesn't give off so much energy, though, that it's not still a viable energy storage medium. So this is an appealing number to see. So these big difficulties are the amount of pressure and heat that are needed to get this process to run. And this requires so much energy and heat that this process alone, the synthesis of ammonia for fertilizer, consumes 2% of all the energy that we use worldwide every year. That's a lot of energy. 2 isn't a big number, but 2% of 16 terawatts is a huge amount of energy. So if we can figure out some way to do this on a much more, much less energy-intensive scale, then that would be certainly be a big boon for the energy economy, and it makes it possible then that we could think about using ammonia as an alternative fuel. So how do we think about doing this? Start with a quote. These folks have. This is a leader in the field of N2 reduction catalysis, and this is writing in a journal from a few years ago, where he's saying that it's remarkable no one's discovered a homogeneous catalyst that can produce ammonia from N2 and H2 in analogy to the Haber-Bosch process. And part of this observation, part of the explanation for this observation, no doubt lies in the extreme inertness of molecular nitrogen. That's really the trouble, is that dinitrogen is a very inert molecule. That's a good thing because it's 80% of our atmosphere, and we don't want that going into our bodies and wreaking havoc. But it's a problem then if we want to think about breaking that bond apart. So the N-N triple bond in dinitrogen is one of the strongest interactions between two atoms known. It's 941 kilojoules per mole for people who are counting. And so then how do we think about activating N2 under more mild conditions than this Haber-Bosch process? One, you can do it electrochemically, and this actually may be feasible if we're able to get plentiful solar energy. If energy production really isn't a problem, then maybe we can use that solar energy to split things like N2. This is still a pretty energy-intensive process. Minus 3 volts is a lot of energy. It's okay, but it's a lot of energy for doing that reaction. Then there are other complications with it that I won't go into. The one thing that really inspired me was looking at how nature does this process and some recent research that's been done on the way nature goes about doing it. So nature splits into at atmospheric pressure, so that's 0.8 atmospheres of dinitrogen, and at room temperature. So that's a pretty big difference from 3,000 psi and 450 degrees C. So if we look closely at what's happening in nitrogenase, maybe we can get some ideas about how to split nitrogen in an easier way. The overall reaction that nitrogenase does up here. So nitrogenase is an enzyme. That means that it has this little this little molecule, this little bit of atoms that are stuck together at the middle of a whole bunch of carbon, hydrogen, nitrogen, and oxygen. So it's this big enzyme. At the middle of that is this little site where we think all the interesting chemistry happens. And the way this works is the N2 comes in. The enzyme has this chain of irons that it uses to deliver 8 electrons. It uses a bunch of magnesium ATPs. So it actually has its own energy-intensive aspect to it. That's a lot of energy in its own right. ATP is what cells use to transfer energy around. And it pulls in 8 protons, and that ends up forming 2 ammonias, an equivalent of hydrogen. So the people have known about this for a long time. What's been found out recently is I'll tell you about here in a second. The way they think this reaction works is that E0 here is this cofactor in a state that doesn't have any added electrons or added protons. And so this E0 state starts adding protons and electrons. It adds 1 equivalent and 2, and 3 and 4, and you get this E4 state, and they think that that's the one that's important for N2 coming into bind. Okay. Importantly here, when N2 binds, people who've been investigating this think that dihydrogen comes off in that same step. And that ends up leaving you with the kind of scenario that you see here, where dinitrogen is bound to a metal that has a lot of electron density onto it. What we're trying to get here is a lot of electron density instead of on the metal onto the dinitrogen, because that's really what's going to allow us to break that nitrogen-nitrogen bonding interaction. And so it's bound to a metal that has a lot of electron density. The current thinking is that that's not really enough, though. And what's really important for reducing dinitrogen and splitting that bond is that you have an electrostatic effect from these protonated sulfide bridges that are right next to the iron. So the cationic charge that's sitting on that sulfur, the thinking is that interacts with the part of the dinitrogen molecule that can accept electrons and makes it easier for it to pull the electron density off of the iron. That's the main thinking now. And that really changes the way that the electron distribution within that molecule, where those electrons reside. So the normal way of thinking about this is that you have a reduced metal and a nitrogen binding to that metal that doesn't have any extra electron density in it. That makes it really difficult to split the bond apart. But the current thinking from this research is that these protonated bridges that are right next to the metal, they help pull the electron density from the metal onto the nitrogen. And that then lets the reactivity be focused on the nitrogen instead of being focused on the metal. So that's a really important idea and the kind of research that we're looking into. Now we're building molecules that can help model this behavior. So we're looking for new chemical structures that can help us evaluate whether or not this is a feasible idea in chemistry and determine whether or not we can get into some new reactivity, like hopefully splitting nitrogen into ammonia and helping fuel the future. So that's a project that I'm interested in. And I think that in general, alternative fuels are a very compelling prospect for being able to store energy from renewable sources and allowing us to get away from fossil fuels. So that's the chemical bond aspect of energy storage, is that we can think about making these alternative fuels to give us a way of decoupling the generation of solar energy from when we want to use it. This other way to do it then is with storage. And here we're going to be looking at this idea of really big batteries. Again, this picture shows what we're thinking about with batteries, and that if you can put an enormous battery in between the solar panels and wind turbines, then the energy that's generated by those sources can be stored in that battery, and then that battery can be used whenever we need it to power the grid in a city. And before I get too far into batteries, I just wanted to give a bit of introduction to them for anyone who's not familiar with how they work. So a battery has a few basic components. An anode in a charged state will store electrons, and a cathode that's where the electrons are going to go to as that battery discharges. So we can take electrons out of the anode that runs through the battery over to the cathode, and then ions get transported across a membrane that helps balance the charge. So as you transfer the electrons from one side to the other, that's creating a charge imbalance, which is satisfied by by cations going in the opposite direction. If we're thinking about new materials for batteries, we can look at the periodic table. So it's a little bit hard to read, but This is a general structure of periodic table. We have, there's one trend in particular that I want to talk about here for thinking about new battery materials, and that's electronegativity. So electronegativity gives you information on how strongly one atom pulls on electron density compared to another atom. So if you look at a single bond between, say fluorine and cesium, if you looked at where the electron density was in that single bond, then you'd see that almost all of the electron density is going to be on the fluorine and on the cesium. That's because we'd say that fluorine is much more electronegative than what cesium is. We can compare that to, say, a carbon-nitrogen bond, which occur all the time in biology. Those are very common bonds. And those are much more covalent. There, nitrogen is a little bit more electronegative, but if you looked at where the electron density was, it would essentially be shared equally between those two atoms. So if we want to develop new materials for batteries, we want to generate the largest possible driving force for taking electrons from one element and moving them to another element. And so we can use these electronegativity trends to get us some information about what a good combination of elements would be. So we wouldn't want to use elemental carbon and elemental nitrogen. That wouldn't work well. We want to use something more like elemental fluorine and elemental cesium. Well, that leads to a few problems with this idea, is that those combinations aren't always practical. So we have these, this is a good guideline. This tells us where these large potential drops are, but sorry, I skipped through a few slides there, but the state of matter and the reactivity of that material, that really plays a pretty big influence on what sorts of compounds we're able to put into a battery for storing electricity. So we look at a grid scale options. There are a few of these combinations that have been put forward as somewhat viable. So we have things like nickel metal hydride, nickel cadmium, sodium nickel chloride, sodium sulfide. These are all element-based batteries that work to varying degrees. What you're really looking at here is a comparison of the system power rating, so how much power a different type of battery can deliver, versus the amount of discharge time. So for our purposes, we're trying to store solar energy for grid scale applications and then be able to discharge that battery over the amount of time that the sun's down. So it needs to be down, it needs to be able to deliver energy during the night. Well, that's hours. So we know that our discharge time needs to be in the hours range. And if we're supplying a grid, then we know that we need to be on a really large scale of really large power rating. So, and the hundreds of megawatts scale. So that limits our possibilities. There are a lot of great options, but a lot of them end up being really difficult to scale to that kind of size. So there are a few that are not based on chemistry that I think are really good options. They just don't work in all cases. So one is pumped hydroelectric. That is essentially you pump water literally uphill, not thermodynamically uphill. In some ways thermodynamically uphill too. But you pump it uphill and then you let it fall back through a turbine. That generates electricity. You can also do compressed air, where you pump air down into a big underground cavern. And then when you want to use energy, then you open the valve, let that run through a turbine, and that generates electricity. Those are great, but there's some geographic limitations to this. So I grew up in southwest Kansas. It's literally flatter than a pancake, so you can't find a hill there to pump water up and then let it run back down. And the same thing with compressed air. There's not always an underground cavern where you need it to be able to store that much energy. So that leaves us with this idea of flow batteries, and I'm going to explain what those are. This is that standard battery diagram that I was showing you, and a flow battery is really very similar. The main difference is that the electricity is stored in the material that's dissolved in these two tanks. So we have a tank has an electrolyte called an analyte, and a tank called an electrolyte that's the catholyte. And essentially you have electrons that are stored over here. And when you want to discharge, then you run those two solutions through an electrochemical cell. The electrons transfer from one side to the other. If you hook up that electron transfer to the grid, then you've got power. So this is operationally a very, very simple setup. There's not a lot to it. The interesting work here then is in developing new materials for the catholyte and analyte. We want to try and increase the amount of energy that's stored per molecule, or really per unit volume, inside these solutions. There are a lot of advantages to flow batteries. They have independently scalable capacity and power. So essentially it just means that you can make the tanks as big as you want, and you can put as many cells in between those tanks as you want. There's a deep discharge profile. We can run those tanks to empty. There's not a problem with that like there is with some other battery systems. Quick response time, safe design, long service lifetimes. These are really a great option. The main limitation here, the main difficulty with this is the amount of energy density. So you compare a lithium-ion battery where you have lithium stuffed into graphite sheets and you can pack a lot of lithiums in per unit volume. You compare that to dissolving some homogeneous small molecule into these solutions, and in this case you have much lower energy density. So the trick here, the game here, is trying to figure out how we can increase the energy density in these solutions so we can make flow batteries a reasonable energy storage mechanism. This is a prototype. This was built in a lab of one of my collaborators. So this is obviously much smaller scale, but these are the solutions they're taking and flowing through this mock flow battery device, or the small scale flow battery device. And they're using that to test the effectiveness of the solutions that they're forming. And again, then this is how we think about using this on a grid scale, is that we can put this massive flow battery then into this grid picture where we're storing wind energy and solar energy. And people actually do this. This is done on a large scale. And these are the two giant tanks. One's holding the reduced material, one's holding the oxidized material. And you can flow those through an electrochemical cell and use that to store energy and release energy when needed. The trouble is just with the energy density, that we need to be able to put more energy in per tank. And that's probably about a factor of 5 over where we are now. So it's not we don't need a huge increase in energy density, but it's marked. And that, if we got to that point, then that would allow electrical companies really to use this as a viable alternative for storing energy from renewable sources. So there are a couple of challenges now that people face in the flow battery research area. The current state of the art is using aqueous vanadium redox flow batteries. So that means that the materials that are in solution are vanadium-based molecules. Vanadium is a light transition metal from the first row of the transition metals. And it's able to go from a +5 oxidation state. It can pick up an electron and go to a +4 oxidation state on one side of the battery. On the other side, it can go between a +2 and +3 oxidation states. And these then are aqueous systems. So those molecules are dissolved in water. Water's great because it's really cheap. That's a really nice option, right? You don't have to pay much for water. But the problem is that you have a limited energy density. So people are working on how to increase the energy density by going to non-aqueous systems. And I'll explain what that means in just a second. These are a number of schools that are affiliated with J. Caesar. That's the Joint Center for Energy Storage Research. That's an energy hub that's funded by the DOE. Just funded it a couple of years ago, I believe. And they're funded to $120 million over 5 years to do really big research on this problem exactly. So there's a lot of excitement, a lot of money, fortunately, and a lot of work being done on how to increase the amount of energy density in flow batteries. And a lot of that work is being focused at non-aqueous systems. Can we move away from water to systems that will allow for a larger energy density? So why do I say water doesn't have a high energy density? This shows different types of materials that you can dissolve in water for electrochemistry purposes. The big thing I want to point out is that the operating range for water is this pink box here, where this is the potential of applied potential to an aqueous solution. So the trouble is that if you go to too positive potential, then you start to decompose water and make oxygen. And you go to too negative potential and you start to reduce water and make hydrogen. Well, both of those are gases which have a pressure problem, and then hydrogen especially is explosive. So that's a big problem for the stability of these systems. And what you get out here is only a little bit over a volt available range. Well, a volt just isn't that much, especially when compared to non-aqueous systems. So we can look at this is a vanadium molecule that people were looking at for non-aqueous chemistry. I think this plot was done in acetonitrile, which is an organic solvent. And really these weird duck shapes that you see here are essentially just a little bit more detail on these individual lines here. They really just tell you at what potential electron is being transferred. And so the window here is much bigger. Just for this molecule alone, the difference in energy between those two couples is 2.2 volts. That's well outside the available range for water. Then not only that, but if you put these on the same scale, so that these numbers match up with these numbers, then you see that one of these is well to the negative, and you can imagine then moving this guy well to the positive of the available water window, and you have a much more energy density. So if you have 1 volt available here, and you could go to another solvent and get to 4 volts, well, then you're 4/5 of your way to that factor of 5 increase in energy density that we need for making flow batteries a viable storage option. The big difficulty is that organic solvents are expensive compared to water. You can turn on a tap and get water, but you have to pay a lot for things like acetonitrile. So if we can get the cost of the materials that are being dissolved in solution to be low enough, and we can get the energy density high enough, then these non-aqueous solvents will be cost competitive with aqueous systems. And so another option for storing, for increasing the energy density in flow batteries, and something that can be complementary with these other techniques, is to store multiple electrons per transfer. So instead of having one electron going into one side of the battery and one electron coming out from the other side of the battery, what if we could set up a situation where we had a really low valent metal getting oxidized by a couple of electrons? So we have 2 electrons coming out of this side, and those 2 electrons going into some redox couple on the other side. Well, that would mean that you just switch out the material that's in those tanks, and you immediately double the energy capacity of that flow battery. How do you think about doing that then? So this is going to get a little hairy. These are orbitals. Don't freak out. Everything's going to be okay. We're almost there, too, so just bear with me. So you notice that this is set up in the general shape of a periodic table. I'll overlay it here to make things a bit easier. Really all we're concerned with in this case is these 5 orbitals here. An orbital is the path that an electron takes, on average, around a metal. So these shapes tell you about where you can find an electron around these elements here. Well, vanadium's here, that's the one I've been talking about. And these elements in general are relatively earth abundant and relatively cheap overall. So those are the ones we're pretty interested in. And these are the orbitals that those electrons go into. And the shape and the characteristic of those orbitals are really important for how many electrons you can store in any molecule that has one of these metals at its core. So don't worry about the labels, the numbers here. The big thing I want to point out is that in this kind of molecule, we can put 6 electrons in these 3 orbitals, and then we have a couple of orbitals that are quite a bit higher in energy. And if we put electrons into those, then the molecule falls apart. Okay? So this is a coordination compound. This has a metal at the center. These things called ligands bound to them. A ligand is just some other molecule. It's often organic, but it doesn't have to be. Plenty of times it's inorganic. And that binds to the metal and changes the properties. It changes how the metal behaves. So if you take salt, for instance, take salt off your table and dissolve it in water, you don't keep sodium and chlorine bound together. Those don't float around in solution as one unit without anything else around. It dissolves, those ions separate to some degree, and you get water molecules coordinated to the sodium. So those water molecules, they bind to the sodium part of the molecule, and just like these ligands are bound to this cobalt center in this complex. So these ligands have they're really important for the way the metals behave. And what they do here, what the ligands do in this case, is they cause this big energy split. They make these energies go much higher in energy make these orbitals go much higher in energy than these orbitals. And then again, the difficulty here is that if you start putting electrons in, you're adding electrons to the metal center, but that's destabilizing the molecule. That's making the molecule fall apart. So from a flow battery perspective, if you started putting electrons into this molecule and that molecule fell apart, you're not going to be able to cycle that flow battery very many times. You do it once, and you're done. So you can put 1 electron in, maybe. 2 is almost certainly not going to work for that kind of geometry, and 3 is right out. So we can maybe get one electron. Very unlikely we get 2 electrons into that kind of molecule. So what we're really interested in is trying to develop molecules that can store multiple electrons, and without that kind of stability problem. And the way we do that is through making ligands, making the part of the molecule that's bound to the metal, making those able to accept electrons instead of the metal itself. This is a relatively recent concept in coordination chemistry. For a long time, people didn't think that ligands could do this kind of redox behavior, where they could accept an electron and release an electron independent of the metal. And we think then that we can use that for flow battery applications. So the idea here, the idea now is that on this energy scale, if you start adding electrons to this molecule, you don't add them to these destabilizing high energy orbitals up here. You instead add them to these ligands, these orbitals that are based on the ligand part of the molecule. So we can imagine adding 1, 2, 3 electrons, and possibly even up to 6 electrons within that molecule. And that should be stable. We don't have the kind of destabilizing effects that you get from occupation of these high energy orbitals. So now you really greatly expand the potential for, pun completely intended, the potential for electron storage in coordination compounds. There's a bit of work that I've worked on with some collaborators at Sandia where we've used this concept in vanadium systems to the same effect. So here we're using this bunch of atoms here as an electron reservoir. So we can pull an electron out of here and form a radical, a single electron on this species, and we can dump an electron back in. We can do that very reversibly, and that allows us to create new materials for flow batteries. So I'll leave it there and just sum up with trying to wrap together what I've been talking about here. So there's this really interesting problem where we have a diminishing supply of fossil fuels, but energy companies don't want to rely on, energy companies keep relying on these fossil fuels instead of relying on the hugely abundant solar energy that we have incident on the Earth every day. And the big problem with that is storage. Without an ability to store that energy, then the output from those sources is really inconsistent. We get variations based off of the time of the year, time of the day, and different weather patterns. That makes it very difficult for companies to be able to rely on this. It makes it economically infeasible for them to use solar energy as the base load for providing energy to their customers. So what I and a lot of other people are interested in doing is trying to develop alternatives for storing the energy that comes from those renewable sources into bonds or into electricity, and then be able to use those when we want to be able to power the grid. And it's a viable path forward both for solving our long-term energy problem, and that we need a source of energy in the next 100 or 200 years. And it also goes a long way towards our climate problem. If we can use this as a way of getting away from fossil fuels, if we can make this technology cheap enough that it makes economic sense for energy companies to use that technology instead of burning fossil fuels, then that will help with the climate change as well. So I'll close there. Thanks very much for coming out tonight, and I'm happy to answer any questions. Thanks. Yeah.
How far away are we in terms of time we could get? Have there been breakthroughs recently? Do you anticipate major breakthroughs in the next 5, 10 years? How many years have we come?
How much money can you give me? Just kidding. I mean, the people who are in J. Caesar, this energy hub, they think that they are very optimistic, of course. That's how they keep their funding going. They're putting a lot of money, a lot of effort into this. So I think it's really feasible that in the next 10, 15 years that we get real traction on this problem. Flow batteries are technology that were developed several decades ago, and they were just left. No one really paid that much attention to it. It's really come back in vogue recently. So I think with the increased focus on it, the increased availability of funds, that will always bring new researchers into the field. And then it's really an economic calculation. My heart drops every time I see oil prices go down. That's just prolonging the problem, right? So a lot of that depends on what OPEC does. A lot of it depends on how much natural gas we produce from the United States. There are a lot of variables that are really difficult to get a handle on. But in terms of technology, I think the technology it's relatively mature. It's getting towards the point where that could be a meaningful technology in the next 10 or 15 years. Yeah. Guy in the back, yeah.
So this might be more a complicated question, but how does time figure into the way that charge?
Yeah, they're really pretty quick. So that's a great point. We call it kinetics, and that's how quickly the energy can be put into or out of that system. And these have very, very quick response times. A lot of that will depend on the specifics of whatever material we end up putting into the battery. It also depends on the specifics of the electrode surface, the piece of metal that's sitting in solution and ends up transferring that electron out to the grid. But in general, they're fast enough that they're viable as energy storage mechanisms.
I heard about these aluminum batteries they're working on now that are really super quick charging. I was wondering if there's any tie-in with that.
No, there's not. Not direct tie in this case, other than that people are really aware of that problem and trying to incorporate that into whatever they're working on. So in a lot of cases, there are sort of two different energy problems. So one is personal device energy storage, in which case we want really fast charge times because I really hate waiting for my phone to charge up. Another great application then is cars. So if we can charge a car much more quickly than what we do currently, then maybe using electric vehicles is a viable path forward. You got to be a little careful there because as it is currently, we're still burning fossil fuels to generate the electricity that's going into cars, right? So that's a problem. But long term, if we can get that energy from renewable sources, that can be a good way to go. In terms of those times, then those are really important considerations. They're not as important in this case, just because the scale is so modifiable. So if we wanted to, if the transferring electricity out of a flow battery was a little bit sluggish, then one possible solution for that is just to make the cell a little bit bigger. Right? So you can increase the surface area inside where the electrochemistry is happening, and that will allow you to transfer more electrons, which can compensate for how slow the process may be. So there are some engineering ways around that in flow battery work, and in general, though, the processes of charging and discharging are fast enough to work for a grid, which is really all that sort of application is concerned with. Yeah. Sorry, I think we had, yeah.
I'm curious what the equation is for the use of ammonia as a fuel. I'm up in the air with that.
Just into it,
yeah. Well, there are two ways to do it. One is to use H2, and one is to use protons and electrons separately. So the way Haber-Bosch does it is to use H2, and that works well when you have that temperature and pressure. In the case of the homogeneous systems that are known, there are a few catalysts that are known now that can do homogeneous N2 reduction to ammonia. Those separate protons and electrons. So you put an acid and a reductant in the solution, put it in with the right catalyst, and that ends up forming ammonia from atmospheric N2. The actual mechanisms by which those go, those are pretty hotly contested right now. People.
The other way, you've got the ammonia.
Burning it. Yeah. It's thought that they know that in burning it you can form some nitrous oxide, so that is a possible byproduct. But the way to actually fix that is to drip in a little bit of hydrazine when you're doing it. Now, people don't want to have a lot of hydrazine around. That's very toxic in itself. But you can have a catalyst that reforms ammonia into hydrazine. So what you could do in line in a vehicle is take your ammonia fueled tank, use a catalyst to form hydrazine that then drips into the fuel, lets the fuel burn more cleanly into nitrogen. Another option then, if that doesn't do it entirely, is that you can have catalysts on the back end, much like a catalytic converter now, that take those nitrous oxides and convert them into nitrogen and water. Yeah.
So a few slides back, you had energy density and discharge rates, and you had listed supercapacitors being at the bottom. But you also listed another type of supercapacitor that had like a slower discharge rate, like the high energy supercapacitors, right?
Yeah.
So what's going on with? I mean, a supercapacitor is an ideal medium. It's very lossless, right? The problem is the discharge rate, but they've figured out a way to slow down.
I'm not sure the details of the technology, to be honest. That ends up getting in the physics literature, and if I venture over those buildings, then my chemistry colleagues start to not let me back into the chemistry. I just don't know the details of technology. I couldn't tell you. I think that's a fair question for sure, but I couldn't tell you the specifics. Yeah. Sure. All right.
You said that ammonia was more compressible. Is that because it liquefies?
Right. Yeah, it liquefies relatively easily. Yeah.
And where is JCES?
The consortium? Yeah. That's centered at Argonne, and then it involves a lot of institutes from
it's basically centered at Argonne.
Right, yeah, right, yeah, sorry.
I guess we're not going to put nuclear fusion into cars. Was that part of this whole notion of how we're going to provide energy at the scale we need to replace carbon sources and so on.
I think that's a it's a very interesting potential application.
Publicity, again, of course,
Yep.
it's been going on for 50 years.
Yeah, right.
Now we're supposedly closer. So on your time scale of how long it's going to take to mature this technology,
Yep.
do you think that nuclear fusion will also mature?
I hope it does. That's a very difficult one to do. The latest that I've heard, which is merely maybe a couple years ago, is that people are still thinking that it's not until the early 2030s that you might get the first initial test as to whether or not fusion is possible. And that's a long ways then from actually being able to commercialize that and make that into something that's sitting where every power plant is to be fueling the grid. So that's a much longer lead time. And I think that's if that ends up working, that's great. It's a very difficult prospect. I think there are a lot of problems there with the certainly with the amount of the environmental conditions that are needed to cause fusion to happen, and also then with the stability of the materials that are housing that fusion reactor. I think being able to do that in theory is one enormous problem. Then being able to actually build a device that can house that is another very big problem. So,
Based on this scale, it's done on a micro scale.
right, and so there's NIF, the National Ignition Facility in Livermore. They use enormous banks of lasers. It's cool. It is really cool. So they have these huge banks of lasers. They take this little pellet of tritium and deuterium, I think, and shoot that up. And at the right instant, all of those lasers, all at once, they clamp down on that little pellet, and they compress it as hard as possible, and you supposedly get some fusion out of that. Well, again, turning that into a commercial process is tough. That's a lot of work. I think it's a great option if it does work, but I think it's still a long ways in the future. Yeah.
You mentioned there was a factor of 5 between the redox flow batteries where they are now. There's supposed to be. What are the metrics that you're using for that factor of 5? Because if it's just maybe you just make the tank bigger, 5 times bigger. So
Yep.
where is the price, or where is the amount of energy it takes to pump? Where is that coming into the calculation?
Yeah, a lot of it has to do with the comparisons of the cost of the infrastructure compared to what's available for fossil fuels. It also depends a fair bit on how you're planning to use that load. So if you look at the load profile of an energy company, the base will be coal-fired power plants. They're new plants that are operating 24/7, and those are providing consistent load. Then there's going to be an intermediate value, say the amount that's needed in the afternoon when use starts to ramp up, and that can be supplied by a number of sources. But then really the part where people think about flow batteries and this sort of technology making an impact is on the very peak, the very last little bit. And that then is traditionally supplied by the aging coal-fired power plants. So technology that's on the out that requires a lot of infrastructure and cost to maintain. That a lot of money is being dumped into it. They're wanting to run that as little as possible so that they don't have to spend any more money on than what's absolutely required. So that's a place where flow batteries could come in and replace that technology. And so the cost in comparison then has to do with the cost of the materials, and both the infrastructure and the actual electrolyte materials that go into creating a flow battery on scale compared to the cost of running those power plants. I obviously didn't do those calculations myself, so I can't give you hard and fast numbers, but that's the comparison that's driving that sort of number.
So if the price of energy went up by a factor of 5, redox batteries would be parity.
That's more or less. Yeah. Yeah.
I thought peak power was supplied mostly by gas turbines.
I think that depends some on. I thought that depends some on location. You may know better than I do on that, but
They can be run up and run down.
Yep.
Quickly.
And I think that's certainly correct. And in other cases where there are aging plants, those can often be used to fill that need as well. Yeah.
Let's stop questions there, and then I'm sure we'll be around for a couple
Sure.
of minutes.
Absolutely.
Let's thank Neil again.
Thanks.